So let's start out by talking about anaerobic digestion. And I'm only starting with this because it goes well with what you're working on in Lab 1. You may be more familiar with compost, so I'll try and draw similarities as we go through if that helps. And just to start with an overview of the process, so anaerobic digestion, so we're in an anaerobic environment, we've excluded oxygen, so we're encouraging the production of biogas, which is a mixture of methane and carbon dioxide, instead of just CO2, which we get from composting. And the key advantage of this biogas recovery is the renewable energy we can generate from it. The whole process takes about 2 to 6 weeks. Composting, as a comparison, is about 3 to 4 weeks, plus there's a curing phase afterward that can go on for a few months. But composting actually goes further than anaerobic digestion, so you have a more stable process at the end. Often you'll compost the digestate that comes out of an anaerobic digestion process. You could also compost the same like SSO or leaf and yard waste food stock going into it. So there's different options, different systems, different municipalities use. So we've got our waste coming in. Coming out of our process, we've got our biogas, as we talked about. We might have a liquid effluent product, depending on if we're doing dewatering or not, and if we're doing like a wet or a dry process. We'll have our solids, which is our digestate. We'll have residuals, so anything we've removed from the process, all that contamination that people put in by accident, we'll have to deal with as well. And then we'll have a whole bunch of odorous air to deal with. And odor is very, very important for all organic waste facilities. We often, or in previous years, went to a facility where you got to smell this firsthand and you would not forget it. But I can't stress this enough. We've got a whole nother lecture just on odor. It's a consideration for AD for sure, much bigger consideration for compost just because of the nature of the process. We'll get into that. AD has been used for wastewater sludge for a really long time. A lot of plants have sludge ADs. For food waste, it's a much more recent thing, and we'll often mix them together in an approach called co-digestion, which we'll talk about. And just harkening back to the first week, the BMP, so that potential of organic waste to produce methane, is a really important metric in AD because it tells us how much methane we can anticipate producing through the process. So here's a little flowchart of a typical facility. So coming in the front end, we've got some feedstock receiving and processing. Similar to a transfer station, it would fall on the floor and it would be inspected and loaded into some pre-processing equipment, maybe some bag openers or shredders. It would be piped into tanks where the anaerobic digestion process would occur. So continuously producing biogas, which would be fed off to a different energy recovery system. And then the digestate at the end would come out and it might be dewatered to produce that liquid stream and a solid stream. It might be kept whole. And then it might go to further processing. So maybe it could be composted or dried, or it could just be marketed as is. And we'll talk about the end product and where it might end up later on in this chapter. So the overall reaction, just to compare composting and AD. So composting, we have a organic on one side, add a bunch of oxygen, and we get CO2 and water on the other side. This is the same as our cellular respiration. Anaerobic digestion, we don't put any oxygen in, so we get methane and CO2 out. But when we burn that methane, we end up with the same overall reaction as composting. So on kind of a greenhouse gas side, they both do the same thing. In anaerobic digestion, we just have this intermediate step if we hold on to the energy for a while in the form of biogas and do something with it. And that's a really key benefit of the AD approach. If you compare the thermodynamics of both of these, you'll also get the same overall reaction if composting versus AD followed by combusting the biogas. So compost, you have this big tower of energy and you go from the top all the way down to the bottom, and you can use that energy to really degrade things to a very stable product. AD, we don't have as much energy to work with. So those microbes in there, they just can't get as much energy as the compost microbes can. So they're doing their best, but the consequence is we have a lot of energy stored in the AD digestate and biogas still. So the biogas, we can use that, and that digestate, we just might further treat later on. And just to visualize this energy that's in the material, on the left side, you can see a flare burning off landfill gas, which is just biogas from a landfill. And the flame really lets you visualize all the energy that's in that methane coming out. As a comparison to composting, on the other side, you can see all this steam coming off the rows. So you don't get this big bang of burning the biogas, but you do get all this drying effect, which uses a tremendous amount of energy, and those piles heat themselves up to over 55 degrees Celsius. So the same net amount of energy. It's just in very different forms in composting, like a biological oxidation versus anaerobic digestion, and then physically oxidizing the gas in a utilization application. So let's look at a little bit of a facility. I showed you the overall steps. So here's the facility. This is the one we normally went to a field trip on. It's BioN in Elmira, Ontario, and they treat municipal and IC&I organics. So if you look at it, you might see some things you recognize. You might take a guess at what some things are. I'll throw some labels on here for you. So kind of just chronologically, if you're bringing waste in, you come in, you've got a weigh scale. Most waste facilities have a weigh scale. We've got a tipping floor and pre-processing area. So all our material will start here, be unpacked, and have a bunch of the contamination removed. This is a wet AD facility as well. So they have a heavy pre-processing stage. Then we've got all these tanks back here. This facility actually uses 2 stages of tanks, and we'll talk about why that is, but there's these 3 little ones, and then there's these 2 big ones. And this last one's actually a storage tank where digestion kind of keeps continuing. You can see a truck over here is picking up the digestate coming out of this storage tank. This particular facility markets whole digestate, so they don't dewater it, it stays as one thing, and it's a certified organic Canada Food Inspection Agency certified fertilizer. So it's like the best fertilizer certification you can get. So they have a really good product, and it's easy for them to transport because of its designation, and they don't have to have a lot of downstream processes. So they have a really good arrangement here, and that's partly because they use this wet technology to make it really clean on the way in. On the front side here of the tip floor building is an odor treatment system. So these are biofilters, which I'll tell you all about. They're full of media with microbes growing on them. Air coming through will kind of dissolve odor compounds into a film of water on the media, and then microbes will eat it, and then they'll emit CO2, which doesn't have an odor. And that goes up this stack and is dispersed. And then one of our other products is our biogas. So at this particular plant, they have a combined heat and power generation plant. So they're exporting electricity to the grid, and they're using some of their heat to run their processes. And they've also got a flare here because all facilities need to be able to get rid of their biogas even if their generators are down. So that's something you'll see at landfills as well, because we're both producing biogas, which it's explosive. We don't want a lot of it around. We need a way to get rid of it. And we'll get into the unit operations in each of these pieces in the coming videos. So the plant we were just looking at is a wet AD facility. If you look at the photo on the far right, that's the type of material that would be in those big tanks. It's pretty soupy looking. We can go a little bit drier than that in a high solids or slurry system. So that's more like an oatmeal kind of texture, 60 to 80% moisture. And then we can go even drier. So something that's really comparable with what would be going into a compost process with a stackable system. And we'll talk about how each of these differs in the reactor design. All of these processes, however, need a nutrient balance. So the key nutrients to balance are carbon and nitrogen. And so the same thing in AD and compost, you want 25 or 30 carbons to each nitrogen just to be able to give the microbes what they need to grow. And we want a pretty neutral pH coming into the process. For contamination, the wet systems, they do a lot of the work to remove contamination at the front end. The philosophy with the slurry and stackable systems is they kind of keep it intact at the front end, digest it, and then go through and sort out the contamination when it's a little bit easier to work with at the back end. So 2 different philosophies. I don't think one's clearly better, but definitely Some of the jurisdictions in Ontario that have targeted really clean digestate from highly contaminated streams have used wet digestion. But yeah, a lot of people like dry digestion as well.